All right, welcome back. Usually I prep each of these slides before I go through them, and I like highlight everything and really kind of get my thoughts together about what I want to say. But I'm going to do it differently for these last couple of videos, and I think we have 2 videos, maybe 3 left in this module. But what I'm going to do here is we're just going to go through it together, and I'm going to show you how I figure stuff out. So I'll occasionally pause the video maybe if I want to draw one of those little diagrams where I do my p-value approach and my critical value approach, my t or z value approach, and might look things up in GPT, ChatGPT if I'm not sure about something. That's what we're going to do. So you're going to see behind the scenes, like how I actually do this stuff before, how I prep, right? How I prep before I record. But in seeing that, hopefully it'll be edifying and help you learn too. So here in these next couple of videos, we're going to learn about inference, about means and proportions with 2 populations. So means and proportions, this is the big thing. So inference is about the difference between 2 population proportions. So the differences between 2 population proportions. What proportion of people like orange juice in America? Right? It's going to be some proportion. There's an exact number out there. And the population's America, and the proportions, the amount of them out of the total that like orange juice, or whatever the proportion is. So we're going to find inferences about the difference between 2 population proportions. So there'll be interval estimation, proportion 1 minus proportion 2 for population 1 and 2, and hypothesis tests about the difference between proportion 1 and proportion 2. So inferences about the difference between 2 population proportions. Interval estimation and hypothesis tests. And so here I might like highlight that for you, right? And interval estimation, and then also hypothesis tests. I might highlight that. And so the first part of this is they give us this formula for standard deviation. And for sampling distributions, they've been calling it standard error, and then having us kind of like figure out that this is actually the standard deviation for the sampling distribution. And so I'm just going to flip that around, and we'll leave it like that. I guess actually that's pretty important. So I would highlight that sampling standard error, standard deviation. And here the standard deviation for the differences between the proportions is this, right? So they just give us this formula where N1 is the size of the sample taken from population 1, and N2 is the same for that. And if you just remember, like, I find it really helpful just to ground myself back down in, like, what are these formulas? And so here you can see, right, standard deviation, how we go from variance for a sample to standard deviation, just the square root of that. And you can kind of compare this, right? So variance is really the difference between some point and the mean, and then square that to get rid of any negatives and sum it all up and divide by n minus 1, and then take the square root of that. So here you can see we're dividing by n, and we're finding, there's some multiplication. But again, this is kind of beyond our pay grade. Like, we're not getting our doctorate in statistics or mathematics, and so we don't really have to be rocket scientists about how did they come up with this formula. It just needs, we don't have to be the engineers who came up with it. We just have to know how to use it. Just like we don't have to be the engineers who came up with the car and all the little parts and how it runs. We just need to know how to use it, right, for our purposes. So same thing here. Here is the formula for standard error, standard deviation for the differences between 2 proportions. So we probably will be coming back to that. If the sample sizes are large, the sampling distribution of the difference between these, so we're talking about the sampling distribution, right? And that's really a pretty important key concept to get around your head, is that if you do enough samples, all of those samples are going to have a distribution, and that's the sampling distribution. Like you'll have one sample if you're measuring a population's mean height, the average of everybody's height in a population. You could do some samples. Well, every sample you do, one sample might say the sample mean of people's height is 6 feet. The sample mean, another sample might say the sample mean of people's height is 5'8". And so if you get a bunch of samples, you're going to get different sample means, and that will create a distribution. You'll have a sampling distribution. So if the sample sizes are large, the sampling distribution, so if you have like 30 or more in your sample size, The sampling distribution of the differences between the proportions can be approximated by a normal probability distribution. So that means we could use the z-table, normal distribution. And if you go back and you look at what the z-table says, here it is. It says cumulative probabilities for the standard normal distribution, right? Standard normal distribution, that's it right there. Standard normal probability distribution right there. The sample sizes are sufficiently large if all of these conditions are met. So the sample size times the probability, the sample size times the proportion is greater than or equal to 5. And the sample size times 1 minus the proportion is greater than or equal to 5. Again, beyond our pay grade, like we're not getting our PhD in mathematics or statistics. We just kind of take it on face value that, okay, that's the rule. And what we're learning here are tools that we can pull out and we can use in different situations. So if we have some situation where we want to do interval estimation of the differences between the two proportions for two populations, then we can do that. And here's the formula for interval estimation of the differences between two proportions for two populations. It's just kind of like, like maybe you have like people from California, what proportion of them like orange juice, and people from Arizona, or Florida. People from Florida, what proportion of them like orange juice? I don't know if that's grammatically correct, but you get the idea. And you can find the differences between those proportions and get an interval estimate to see if, hey, how big is this difference with a certain amount of confidence between Florida and Californians, the proportion of them that like orange juice. And then you could use that for marketing purposes, making more money, which is kind of what it seems to be so all geared towards. A tax preparation firm is interested in comparing the quality of work at 2 of its regional offices, right? 2 of its regional offices, quality of work, by randomly selecting samples of tax returns. So samples, I'm just going to highlight that because why not? Prepared at each office and verifying the sample returns accuracy, samples accuracy. So that's like the other part of it. The firm will be able to estimate the proportion of erroneous returns prepared at each office. So proportion of erroneous returns, right? And I guess I'll highlight this whole thing, right? It's kind of like all of that's important. And then usually at this point, I'm like, oh, I don't want that stuff down there. So I go to slide, I go to edit theme, I click on this main one, and I choose, oh, I actually clicked on the wrong one. I go to slide, I go to edit theme, and I click on that one, and I say, I don't want that, I don't want that, and I don't want this, because it's just like cognitive, in education, they call that cognitive load. And it's like unnecessary information your brain doesn't need to process. And you might say that I'm giving you more cognitive load here by showing you behind the scenes a little bit, but I actually think this is good educational content. And so usually they have like this stuff on 2 slides. So I'm just going to copy this because I think this could just go right here. And then I'm just going to reduce the size of all that. So take all that. And I don't have my font, so I have to kind of take it all and just bring it down a little bit. And so I'll do that. Come on down. And we'll just put it here. And then I'll grab this and bring it to here. And then I'll grab these, all this stuff here. And I can't get all this without getting that. But it looks like those are all separate. So I could click them individually. I could click all that. And then I could just move this stuff a little bit. And the bottom of my slide's right about there. Close enough. I like it. So I don't need this in there anymore, so that'll give us a little bit more room. And then this could come up, and then these can come up a little bit. All right, I like that. So independent random samples from 2 offices provide the following information. So for me, like that's just easier to make sense of the problem. I put it on one slide like that. And we have office 1, the sample size. So, we're pretty large here. So central limit theorem says if we have a sample size that's large enough, we're going to approximate the normal probability distribution. And I'm thinking, and usually that's spoken about, central limit theorem talks about sample size being large enough at 30, and we're at 250 and 300, so I think we're good. And number of returns with errors, we have this. And so here we could calculate a proportion. So if we wanted to calculate this proportion, I'll just get like another little text box. And I'll put like that right here. And I'll just make it really small. So I'll go down to like 10 or even 8. And I'll just say 35 divided by 250 is equal to, and then I'll go calculate that because I can't do that math off the top of my head, and it's 0.14. And so that's not the one I want. This is it right here. It's 14% is the proportion. And then I'll take this and I'll copy it and I'll paste it and I'll bring it over here. And we have 300 over, or 27 over 300, which is going to be like, it's going to be like 9%. So let's just copy that. And it's 0.09, just had to verify it. And we have 9%. Okay, and so just like right off the bat, the differences between these is going to be 14 minus 9, 5%. And there's going to be some confidence level, probably, that we'll want to calculate this with. Oh, here we go. 14 minus 9 is 5%. So proportion of erroneous returns for population 1, proportion of erroneous returns for population 2, P1, P2. Sample proportion of random sample from population 1. Oh, so this is the population and this is the sample. So here's where I'd highlight that, but I can't because for whatever reason, like the people who create this presentation, they just put images in, which is wacky. So if I wanted to do these, I would have to come in here and get a box, and I'm not going to do it. And then I put a box around this, and then once I had the box around it, I'd say I don't want any fill. So I'd get rid of the fill, and I'd say I do want some border, and I want that border to be like yellow, and I want it to be 8. And I could do that for population. I guess I am going to do it. And then we could put that there. And then I could also do it for sample, and I could put that here. And that way it's just really clear what we're looking at here and the difference between population and the sample, the proportion, right? So the sample proportion for a simple random sample from population 1 and proportion of erroneous returns for population 2, so sample proportion. All right, so tax preparation firm for alpha is equal to 0.1. So our alpha is 0.1, which is not 0.01, which would be 1%. 0.1 is 10%. And for a z of 0.05, and z of 0.05 tells me that's alpha divided by 2. And so that tells me like, hey, this is a two-tailed test. I mean, just kind of like reading how they kind of put it together here. And if we go back and we look at this, here's our interval estimate. Okay, and so I'm going to take this formula here. I'm going to copy it, and then I'm going to come back to, we pretty much did everything here. That they did here, we did it all here. And so if I put this formula like right here, and I'm just going to bring it over here, and I'm going to make it smaller so there's room. And now hopefully you can still see that, right? But that's just like a little reminder. Here's our formula. But where do we get our data? So here's our N1, here's our N2. We have N1, we have N2, and then we have P with a bar over it. And so P with a bar over it, it makes me think of like X with a bar over it, and X bar is our sample mean. And so here, if I bring up our notation, X bar is our sample mean, and we'll keep this right here. So there's X bar, it's our sample mean, and we have P bar. So that's our sample proportion. And so here's our sample, and our proportion here is like 14% and 9%. So we have 14% times 1 minus 14%, and 9% times 1 minus 9%. And so if we look at this formula here, 14 times 1 minus 14, 9 times 1 minus 9, and then our N1s. And then the only other thing we have to figure out is like our Z on this formula here. We just have to figure out that Z. And plus we have this range right here. And so that range is going to be, again, 14 minus 9, 14 minus 9, right? So we're just using the formula, but how did we figure out our Z? So nowhere in here did they tell us the confidence interval like what is our level of confidence, right? So our level of confidence. And I like this slide. I pretty much put this slide in all of the slide decks so we can come back to it because this vocabulary is important. And so what is our confidence interval estimate? What's our confidence level? Sorry, what's our confidence level, our confidence coefficient? And so I'm just going to keep original, it's fine. So our confidence level that we could see here from their calculations And I don't see that here, like with what confidence level. So I might add, like just copy this, and then independent random samples from 2 different offices provide the following information, and proportion provide each office with alpha equal to 0.1, right? Because that's pretty much what they do here is their alpha is 0.1, but they don't tell us that anywhere. So this is 90% confidence interval. And because it's plus or minus, we're kind of looking at some sort of a sampling distribution. It's going to be a normal distribution. And because it's plus or minus, it'll be two-tailed. So it's z over 0.05, which is alpha divided by 2. And so what's our z table? So we go and we get our z table. So here's our z table. And I'm just going to put it over here. So here's our z. And I'm just kind of piecing this together here. And this is kind of like our page with all the data. And we have 0.5 over here, right? Because if alpha is 10%, we have 5. If it's 10%, we have 5% in each tail. So if this is 5% right here, then this is going to be 95% of our data to the left. And so I'm looking for 95% of our data to the left, and it's right here. It's between 0.9495 and 0.9505, and it's actually right in the middle where that x is. And so that's going to be 1645, and they have 1645 right there, 1645. And so now we've got all these pieces, and we could get 0.05 plus or minus 0.045, and we could say the 90% confidence interval for the difference in the population, the 90% confidence interval for the difference in the proportion of erroneous tax returns prepared by 2 offices is that, right? So the difference in the proportion in the population of erroneous tax returns prepared by the 2 offices is 0.05 to 0.005 to 0.095. And so that would be like less than 0.5% to like 9%. So about between 0 to 10% is what we're looking at for the difference in the proportion of erroneous tax returns in the populations prepared by these 2 offices. So that's creating an interval estimation for the differences in proportions for 2 populations based upon samples to estimate and make inferences about the population's proportions. Geez Louise, man. How do you say sprinkled donut in French? That's what we're learning here. We're learning the language. All right, so I'm going to call this video more than good. I'm going to call it excellent. And I'll see you in the next video.